Thank you for joining in and being a part of this evening. This is Sonali Chauhan on behalf of TCS ION, and I welcome you all to this masterclass where we'll talk about masterclass on 12-bit asynchronous SAR ADC. In today's fast-evolving tech ecosystem, the demand for high-performance, energy-efficient, and compact devices is driving innovation across industries. And at the heart of this lies VLSI, very large-scale integration. It's enable advanced system-on-chip design. This exclusive masterclass on 12-bit asynchronous SAR ADC in collaboration with IIT Hyderabad will take you through the essential of modern analog design, focusing on how SAR ADCs are built with asynchronous operation to deliver higher efficiency, lower latency, and improved performance across real-world application. Also, we'll talk about VLSI Chip Design Program in collaboration with TCS ION and IIT Hyderabad, a unique opportunity that gives you an edge with industry-relevant knowledge and expert guidance to stand out in today's job market. So whether you are a beginner or exploring the field or someone looking to build a strong foundation, this session will equip you with the essential knowledge to navigate the world of semiconductor design. And we are delighted to welcome Professor Ashudeb Dutta and Shriya Shukla from IIT Hyderabad, who will be leading this insightful masterclass. With extensive expertise in VLSI chip design, they will walk us through the fundamental and deep dive into the design of the topic which we have today and helping us connect with the theoretical concept with real-world application. So before we actually start, let me introduce both of them to all of you. Professor Ashudeb Dutta is a professor in the Department of Electrical Engineering at Indian Institute of Technology, Hyderabad. His area research includes analog and radio frequency IC design, wherein Shriya Shukla, she's a MTech research assistant in microelectronics and VLSI in IIT Hyderabad. And with her research interest is custom designed digital design. So a very warm welcome to both of you. We would like to understand from you that in the electronics and semiconductor space, many specializations are driving innovation today. So could you share where VLSI stands in terms of importance and relevance? And more specifically, why analog IC design and ADCs, especially the topic of today's masterclass, 12-bit asynchronous SAR ADC, are so significant in current context?
Just add you last, I think 2 lectures we cover in the webinar. One is the pipeline ADC, one is the Sigma Delta ADC, and this is the third is the SAR ADC we are covering. The reason behind that the ADC is one of the things which is a very essential part for analog and digital connectivity. And there is analog connectivity is there and there is a digital connectivity is there, not only as a connectivity, also the design block contain analog idea as well as digital idea. So also mixed signal idea. So this is the whole chip design company who are working on the semiconductor chip. They require either analog designer, either digital designer, or mixed signal designer. So digital designer has a, if you look as a core designer, then after that core designer, there is a peripheral designer, and there is a software designer. Okay, so all skill is involved if you are able to fundamentally you understand digital design. So that's why the VLSI domain, this ADC we are covering today, SAR ADC. So you will be, when you go through that lecture, you find out how digital connectivity and analog connectivity on there. And this help you in the future whenever you come to this kind of our certificate program and our bootcamp, you have to get a lot of understanding how this has been designed.
Right. Thank you so much, sir, for the wonderful explanation. Shreya, I would like to. Would you like to add anything in this in this answer?
As Satat has covered everything, but I would like to add that in real world, every signal we have, everything is analog. So, but the processing we do is in digital. So to connect the real world to the practical world, to the chip design world, the ADCs are a very important part, as well as the digital to analog converter, which I will tell you about today.
Great. And we can't wait. Thank you so much, Shreya and Ashudeb for the clear and insightful explanation. You have beautifully highlighted how VLSI chip design with its blend of digital fundamentals and analog circuits form the backbone of modern electronics. So with this encouraging note, let's now explore this subject greater in depth. So over to you, Shreya. Please take us through the wonderful masterclass.
Thank you, Sonali. I will share my presentation. Hello, everyone. Welcome to this webinar on successive approximation register ADCs, that is SAR ADC. I will cover working principle of SAR ADC along with their practical implementation. I will also introduce different architectures, which further helps in improvement of SAR. Before diving in, let's remind ourselves that everything in the physical world is analog. Sounds, temperature, images, everything in the physical world is in smooth continuous signals. But computers, smartphones, and digital systems don't understand that. They only understand binaries, ones and zeros. So how do we connect these two worlds? Through analog to digital converter, or ADCs. They act as translators, taking real-world signals and converting them into digital data. If you have ever made a phone call, listened to a music on your earbuds, or measured your heart rate on smartwatch, you have depended on an ADC without realizing it. So we will start with one very popular type of ADC, which is SAR ADC. Think about the devices you use every day. Your smartphone microphone records your voice. Your camera captures light. Your smartwatch monitors heartbeats. All of these signals are analog or continuous in time and amplitude. But the processor inside these devices process the digital data, not the analog data. It is more efficient to process on digital signal. That's where ADCs step in. They bridge the gap between the digital world and the analog world. So let's break down the ADC into 3 steps. So ADC has 3 steps for conversion. The first one is sampling. This is like taking snapshots of a moving object. Instead of recording the entire continuous wave, the ADC measures the signal at discrete time intervals, which are fixed time intervals. I think all 50% of you are from electronics background, so you must know that the sampling rates, the Nyquist theorem, states that we need to sample at least twice the highest signal frequency to avoid losing information. Then the next step is quantization. Now, once we have taken a sample, we need to map it into the nearest available digital value. Then imagine dividing a ruler into fixed marks. The more the divisions, the finer the resolution. This step introduces a small error called quantization, but this error is unavoidable. Then the third step, which is encoding. So now, once we have taken a sample, we need to map it to the nearest available digital value. Finally, the quantized values are expressed in binary numbers. So they can be processed, stored, or transmitted by digital systems. So that's why the quantized values are now encoded into digital bits. Without this chain of sampling, quantization, and encoding, our digital devices would be blind to the analog. So all the ADCs contain these 3 crucial steps. Now, how these steps are divided in SAR ADC, we will see in the next slide. This is a block diagram of SAR ADC. I'll get to it. So SAR ADC why is it special than the other 2 ADCs, which Sir has also mentioned. We have talked about flash ADC. We know which is the fastest. We know delta sigma ADCs, which is the most accurate. But what about SAR ADC? It gives a great compromise, which is why you'll find in so many medium speed, medium resolution applications like wireless communication, IoT sensors, and portable devices. It balances speed, resolution, and power efficiency. So it's best of both worlds. How does it work? Then it works on binary search algorithm. Most of you must have an idea of binary search algorithm. It divides our range into half and keeps doing it until we get our final result. So here's the key idea. See, this SAR block is SAR, we call it SAR logic or SAR register. This is our DAC, which is digital to analog converter. Then we have a sample and hold circuit and a comparator. This is how we make a SAR ADC. These are the crucial blocks which are in the SAR ADC. Now, we start with the input signal. We take our input signal, we give it as an input to the sample and hold circuit. Then it samples the input signal at equal intervals. Now, what SAR logic does is it starts by assuming that this are suppose n bit this is n bit SAR ADC. So this dn minus 1 is your MSB. This T0 is your LSB. So the SAR register starts by assuming the most significant bit is 1. So dn minus 1, it assumes that is 1 and all other bits are 0. So what happens? It has divided the n bit range into half. Now the bits are acts as the input to the DAC. Now DAC converts this input like this input to an analog output corresponding to the digital bits we have given it. So 1000 is converted to suppose if our range is from 0 to VREF, it is converted to VREF by 2. Now Vin, the sampled signal we have at the output of sample and hold is compared to the generated analog voltage from DAC. Then if it's higher, the comparator value it's higher, then the SAR resets the bit to 0. If it's lower, the SAR keeps it as 1. So if the assumed voltage of SAR is lower than what we needed, which is Vin, then it remains as 1. It keeps this dn minus 1 as 1. But if it is higher than what we needed, then we need to take it down a notch. So what we do is the SAR logic makes this dn minus 1 as 0. See, I can give you an analogy. Imagine I ask you to guess the number I'm thinking of, which is between 0 and 15. You start with the 8, the middle number. If I say that is too high, you cut the range down. If I say that is too low, you cut the other way. Within 4 guesses, you will be able to guess the number of what I'm thinking. That's exactly how a 4-bit SAR ADC works in 4 comparisons. It finds the closest digital code to the analog output, and this iterative step-by-step refinement is why SAR ADCs are both simple and efficient. Let's go through this flowchart so you'll get a better understanding of how SAR ADC works. What SAR logic does initially, as soon as we get a sample, it generates this digital bits 1000. Now comparator checks whether this VDAC is greater than Vin, that is the output of digital to analog converter is greater than Vin, or is it less than Vin. If VDAC is greater than Vin, then we don't want that. That's why we make this 1, the MSB bit 0, and we check with the next bit. And if it is less than Vin, then what we do is we keep the bit as 1, and we also check with the other bit. So we make the next bit also 1. This process goes on until and unless SAR logic has assumed 1 for all the bits and has converted to a corresponding digital output. See, you can see here it goes 0. If it is again VDAC is again greater than Vin, it again becomes 0 and it makes the next bit 1, and so on. However, if it is higher, then if it is lower than what we needed, then we keep this bit as 1. We have already decided for MSB. We are checking for the next bit. So we keep this bit as 1, and we again check with the next bit, which is again we make it 1, and the next bit remains 0, and so on. This is the basic principle of SAR ADC. Let's go with the next slide. Here I have included a video of showing you how it works. So we start with 1, we make this bit 1, again 1, and then 1. So in this 4 steps, you can see we get the final output. You can see this. You can see this graph, how it is converting every input voltage to the corresponding output digital bits. 1 by 1, first, if it is too high, it goes low, again goes high, again goes low. See, here it goes low. If it is high, it again goes low, it goes low. And we get the final output at the end of the conversion cycles. So let's start with the practical implementation of how SAR ADC works. Now, these are the 2 practical implementations. I will once start with the convention and then move on to monotonic SAR ADC. Here you can see this is our comparator. Again, this is SAR logic, which generates the digital outputs. This output of SAR logic goes goes to this deck. This is our deck, C deck. So how does it convert? How does it work as a C deck? You can see here the switches are there, which will connect either to VREF or to the input signal. Here at the top plate, we'll connect the common mode signal. Now, initially, we take our input signal, we sample it on all the capacitors. Let me first go through this capacitor. So this CDEC is twice of the last capacitor value. So if this is C, this is 2C, 4C, 8C, and so on. So initially, during sampling, we connect this common mode to the comparator inputs at both the sides. And we connect V input at the bottom plate of the capacitor. As soon as we are done with the sampling, we start connecting SAR logic output bits to here, to these switches, either VREF at the top node or VREF at the bottom node. So you can see there are, if it is visible, there is one ground and one VREF attached to all the capacitors. I will take a pointer so it will be visible. So this you can see this is a ground, this is a VREF. These both lines go to all the capacitors. So as soon as we are done with the sampling, SAR logic will make the MSB bit 1, which is, let's assume, is B10. So this C11 is MSB. It will connect C11 to the MSB, that is VREF, and all other capacitors, it will connect to the ground. And the same opposite of what is happening here will happen here. It will connect MSB to MSB with, that is C11, to ground, and all other bits to 0, because these are complementary signals. One is going to the positive end of comparator and other is going to the negative terminal of the comparator. So that's why we connect it in the complementary manner. So this left side here, we have the flow of conventional SAR ADC. You can see we start by first connecting VCM. Here we have connected V input, and here we have connected V input negative to all the terminals. Now we remove this. We connect VREF here. We connect ground to all other terminals. This is your MSB, 4C. So C is your LSB. Again, this is, I told you, this is complementary. So this will go to ground and all other are connected to VREF. We make our first comparison. If we see if comparator output is 1 or 0. If it is higher, if V input minus V is greater than 0, we keep the VREF, which was here to here, and we make the next bit. This bit 2C to VREF. We connect it to VREF. So how are they coming? They are coming from SAR logic. SAR logic is deciding whether this will remain VREF or it will go to ground. Similarly, if it is lower, if VIP is less than V, we make this ground. It was VREF here, and then it goes to ground, and we make the next bit VREF, the next bit, that is 2C VREF. Here, these are again complementary signals. So as you can see, at every step, we need to do switching twice. Once at the top level, once at the bottom level. So due to switching from VREF to ground and ground to again VREF, there is a lot of power dissipation. There's a lot of switching power which is burnt. So the researchers have come with another design, which is called monotonic SAR ADC. What monotonic SAR ADC does is it only switches one capacitor at a time, not two. So it reduces the energy by 80%. So for example, for conventional SAR ADC, capacitors are switched in a trial and error manner. At each step, multiple capacitors may toggle. Maybe the MSB bit we are checking, and the next bit we also want to make it one. If the comparator's guess is wrong, those toggles waste energy. And but in monotonic switching, only one capacitor is switched in each step. No toggling back and forth. Energy consumption, that's why it gets reduced. Now, digital control logic also gets simpler. It results in a low power, simpler logic, and more efficient operation. This innovation makes IDC more suitable for energy constrained devices like IoT sensors and portable electronics. Here you can see the switching of monotonic. Here we were sampling V input at the bottom plate of capacitors. Here we are sampling the input at the top plate of capacitors. We have also removed the common mode signals. So the common mode of the comparator will also keep changing. We start by keeping all the bits to VREF. at both sides. Now we check the comparator output. As soon as we are done with the sampling of the input, we check the comparator output. If it says that VIP is greater than VIN, then we switch this VREF to ground. Here we were switching both of them. It was this VREF was going to ground and this was going to 0 to VREF. This is VREF to 0. Now you can see that from here we are making VREF to ground, but not making this VREF to 0 or anything. This remains same. So power consumption is reduced. Here further you can see that 0, again we will check for the next bit. We input my scene. Again we'll check whether it is greater or not, and we'll keep doing it until we get our final output. This reduces 81% of the energy which was burnt in conventional SAR ADC. Also, I would like to mention that bootstrap switches are used in monotonic SAR, which increases linearity. So I would like to hand over the meeting to Sonali for a bit, then I can continue. Okay.
Sure. Sure. Thank you so much, Shriya, for walking us through the first half of the session with such clarity. It was wonderful. The practical example shared, the example of smartwatch, which everyone actually you are using nowadays, everyone. So I think it will truly help in simplifying complex concepts like and making them more relatable. So I hope all the participants have not missed this opportunity to note down the key points from the hands-on masterclass session by Shreya. So I can see there are questions coming up from the participants. So audience, please put your questions in the chat and we'll surely be addressing all the questions very soon. But before that, let's move on to the most important part of today's session. The reason we are conducting this masterclass is not to share the knowledge, but also on the talk about the exciting topic and introduce you the program behind it. So this program is designed to help you prepare for the future and make the most of the upcoming career opportunities. As a part of our commitment to bring you the best career opportunities, we are thrilled to present an exceptional program launched by IIT Hyderabad in collaboration with TCS Ion. So everyone, this is a 2-month certificate program by IIT Hyderabad. It includes over 40 hours of world-class experimental learning. You'll also get a chance to attend 1-week dedicated boot camp at IIT Hyderabad for hands-on exposure. This program gives you the access of live lectures, industry tools, and sessions with IIT professors and experts. In terms of eligibility, so if you are a bachelor or master's student aiming for career in electronics, even if you are interested in the research in the VLSI domain, the program is designed for you. It helps you build a strong foundation and fundamentals and even equip you with the knowledge to run startup. Talking about career path, so as you can see on your screen, once you complete this, you can look at roles such as VLSI design engineer, physical design engineer, analog design engineer, layout engineer, verification engineer, even test engineers. And the average salary range is in the field is 7 LPA to 12 LPA. We move on to the next slide, Swapna? So now coming to the details, the program is very hands-on. You'll work on the tools like Cadence, LT Spice, and Mentor Graphics. You'll design and you will design and stimulate analog blocks, test benches, and also verify digital circuits, and which all are directly needed in the industry. This program is taught by some of the finest faculty from IIT Hyderabad, Professor Ashudeb Dutta, which is here today with us, and Dr. Gajendranath Chaudhary, Dr. Abhishek Kumar, Dr. Kapil Jainwal, and Dr. Rajesh Kedia. The courses start on 8th of October and ends on 29th of November. And right now, there is a launch offer of 49,160 rupees, so which is inclusive of all taxes. So for those who opt for the 1 week boot camp, there is an additional cost of 9,440 rupees to guide us through the remaining part of this insightful masterclass.
Thank you, Sonali. I will share my screen.
Sure.
I hope the screen is visible.
Yes, it is visible.
So after making conventional SAR ADC, improving the energy efficiency and making it monotonic ADC, researchers have further find a way to increase the speed of ADC. How do we do that? They have introduced two types of SAR logic. So the SAR logic, which is generating 100, then again 010s and so on, the digital bits. We can improve the speed of SAR logic. How can we do this? There is one synchronous SAR logic and there is again asynchronous SAR logic. So this figure you are seeing, it compares bit cycling time. Meaning there's two phases of SAR ADC. One is the sampling time in which it samples the input voltage, and the other is bit cycling time in which it converts the input voltage into the digital outputs. So this diagram, it shows how bit cycling timing in synchronous and asynchronous SAR logic works. So this top one, you can see this is for synchronous, this graph. This is your sampling clock. Here at the high end of this clock, we will take the sample of the input. And during the low of the clock, we will convert our input to the digital output. Here you can see this is for synchronous SAR logic and this is for asynchronous SAR logic. So what is the difference between them? In synchronous SAR logic, it is controlled by a global clock. Here you can see it is a clock with the same frequency. We generate this clock from the outside, not inside our cycle. So this we use a clock generator, or we can maybe use frequency divider to generate this clock. Now this is a very high frequency clock. For each bit decision, suppose let's take 6-bit SAR ADC example. So if we want to convert 6-bit SAR ADC, for each bit we need one clock cycle. So in this step, the first clock, D6 will get converted, that is MSB. In this second step, we will get the D5 bit and so on. Now, there are multiple phases of synchronous SAR ADC. The first part, this is our track. You can see here, this is track and hold. So at this point, our input tracks the sample and cycle tracks the input and holds it to a constant value. Now, this means that comparator makes a decision. So when we get our input, comparator decides whether the input is higher than our VREF by 2, that is higher than the middle voltage we have taken, assumed from the SAR logic, or it is lower than this. So comparator makes a decision. Now the second part is latch. Now comparator gives a decision, and we need to latch this decision. We need to store this bit so that we can finally, after all the 7 steps are done, we finally give this bit as the final output. So the second step is latch. Now the third is DAC cycling. So as we know, after every cycle is done, SAR changes one bit. So if SAR changes one bit, it goes to whenever SAR changes one bit, it goes to the capacitor directly. Now, if it goes to the capacitor, what happens here is we apply the principle of charge conservation, and charge sharing is done between all the capacitors. It's not like we will store, if we connect VREF here, this VREF will charge only this capacitor. This charge will get distributed along all the area of all the capacitors. So this distribution takes some time that we call as DAC settling time. So some time is taken in that. Then we keep a timing margin also. So that if our circuit, if comparator is working slow, if latch is working slow, if any of the circuit is not working accordingly, then we need to keep the margin so that all the DAC bits get settled. All the charges distributed correctly. So this thing keeps going on for all the 7 bits. And you can see for all the 7 bits, it takes equal amount of time to do all these 4 steps. Now, 3 steps and 1 margin. Now, this takes a lot of time because we have to wait for comparator, then we have to wait for the latch to happen. Then we also have to wait for DAC to settle. So if we don't keep all this time, it may not give us the correct output. Also, we need to keep some margin if our circuit doesn't work properly, if it is slower than what we expected. this is your synchronous logic. Now, what happens is asynchronous logic. So this clock you see, this is not a global clock. This is a clock of asynchronous SAR logic, and this we generate in the circuit itself. How do we generate this? We use the comparator output to generate this. So we use a differential comparator which has basically two outputs also. Now the comparator output is only valid that with the differential comparator, the output is only valid if its output is one bit is one and the other is zero, or the second thing is either first one is zero and the other one is one. So the comparator gives a valid signal. The comparator tells us itself that whether this output is valid or not, whether I'm done comparing or not. So comparator takes some time in comparing or not. Now the output tells us to reset the comparator now again, because we need to compare the next bit also. So comparator gives some valid signal, which is again used to reset the comparator. At the same time this is happening, we latch our outputs and we do the DAC settling also. So as soon as we latch our output, SAR logic works, and we start with the DAC settling also. At the same time, comparator is resetting. So this comparator is itself using its own signal to reset the SAR logic. So because of this, the time to do this vary in every bit conversion. So sometimes it may take a lot of time, and sometimes it may take a little bit more, sometimes it may take a little bit less time. It depends ultimately on comparator, and we depend entirely on the comparator output to further further do the next step. So we don't start with the next step until and unless we get a signal from comparator. This makes us, you can see this if we use a synchronous logic, it takes a lot of time. But asynchronous signals, because it depends on a circuit itself, the circuit can tell itself whether our comparison, our latching, and our DAC settling is done or not. That's why it takes a lesser time. Because here you can see sometimes we have given equal amount of time for all the bits. Sometimes it may happen that it has done the comparison earlier, but because we have assigned some time, it will not start with the next step as soon as the time period is over. So in asynchronous, we don't give a fixed amount of time for every step to complete. We try to give the decision to the circuit by the circuit itself. That's why it becomes much faster. You can see it's basically done in third, fourth of what we were doing in synchronous logic. It may sometimes also get increased. It may sometimes decrease also. So again, we give some margin. This margin we can decide, and we can make it lower also. This basically increases our SAR logic timing. Decreases our SAR logic timing, and due to this, we can sample the circuit much faster. Because if here our conversion is done, we can again give one clock and sample the next output. So the conversion becomes much faster. Let's move on to the next slide. I hope this was clear. So this is a circuit of SAR control logic, asynchronous SAR control logic. You can see it's basically like a digital block because it has just 3 flip-flops. This is the signal from the comparator. So this valid signal, as soon as comparator says my output is valid, it goes to all the D flip-flops. So this clock is your sampling signal. At this point, we take the sample of our input. Now clock sees the clock comparator. So our comparator is also clocked. So it works only when the clock goes high. Now, and valid is the output of comparator. So it generates one clock and it gets one clock. Now, after every clock of the comparator, for every decision, this is the figure for a 10-bit SAR ADC. This is 10 steps. So for every decision, it generates one clock. You can see it generates total 10 clocks. So this clock again goes to 10 flip-flops. 10 clocks goes to further 10 flip-flops. As soon as this clock goes high, the first flip-flop, the MSB flip-flop, will store the comparator output. In the next clock, it will again store the next comparator output. So at the end of all these cycles, we will get 10-bit from the latches, which is our basically corresponding digital output for the analog output input. Now, comparator is also a very important part because the faster the comparator is, the faster it can make decision. So it plays a huge role in SAR ADC performance. So if you're going with a monotonic SAR ADC and if you're using a asynchronous SAR ADC, then you should use a faster comparator also. You can make it more energy efficient. You can make it more efficient. You can make it. You can speed the process further. So people go with the dynamic comparator. This comparator is the decision maker basically. It decides each bit. So you can see these are the inputs of the comparator. These are the two outputs. This output goes to an AND gate, and we if at every time comparator makes a decision, maybe it is 1 or 0 and 1 or 0 or 0 or 1. So whenever this is 1 0 or 0 1, well, it becomes high. And when the comparator is not comparing, both of them are 1 and the valid goes low. So dynamic comparators have become popular because they consume no static power. They only draw current while switching. So this helps us a lot. Now let's go to the next bit. So we have bootstrap switches also. So why do we need bootstrap switches? In ADCs, linearity is also very important part. So bootstrap switches, what we do is it is used in the sample and hold stage. The challenge in sampling is that transistor resistance can vary with input voltage. This can hurt the linearity of our ADC. We want our ADC to be linear. So bootstrap switches keeps the gate source voltage constant. This means resistance stays low and steady, gives high linearity and wide bandwidth. Together, these all the blocks, the comparator, dynamic comparator, the bootstrap switch, and asynchronous SAR logic, monotonic switching, this results in maintaining very low power consumption. Now you can see here is the diagram of the booster switch. Here we can use a voltage source to keep the gate to source voltage constant. But we cannot use multiple voltage sources here. So that's why we instead use a capacitor which stores VDD. How do we store VDD? We connect it to a switch which is directly connected to the power supply. So either in one phase we charge a steel capacitor to the VDD. In the other phase we supply this capacitor value, VDD value, to our gate of the switch. Here I have included some simulations results for SAR logic, some simulation results for the SAR ADC I have designed under the guidance of Dr. Ashudeb Dutta. So you can see this is your SAR logic. This only has flip-flops. Only using these flip-flops, this basically works as a digital schematic. So it only has flip-flops. You can design using just digital knowledge. Now here is the C deck. You can see this is one capacitor. This is another capacitor. So C2, C4, C, it goes on like that. These are your bootstrap switches. This is done to do the sampling. This is again the simulation results of the SAR ADC I've designed. You can see this is the analog output of the. So basically, how you design it, how you check if the results are correct. So you start with an ADC design. You get some digital output bits, but you cannot for a sinusoidal signal. You cannot check for every code. Okay, my input signal is this. Now I will check the corresponding digital output whether it is correct or not. So we again give it to a ideal digital to analog deck. So what it does is it converts the digital bits again to an analog signal. So this we do using the ideal deck. So you can see this is like output of deck signal, and here we have calculated ENOP for 1.875 megahertz. ENOP for 12-bit IDC, I've got 11.6 ENOP. So ENOB is your effective number of bits. It's not possible if I'm designing 12 bits IDC, it's not possible to generate effective ENOB as 12 because of some non-idealities, because of switching issues, due to capacitor mismatch effects. It is possible that our ENOB gets reduced. So usually it is between 10 to 11 bits for a 12-bit SAR ADC, which is designed. So these are some references. If you want to further read about SAR ADC, you can go through with this paper. It gives a very detailed explanation of monotonic SAR ADC. And this is a lecture you can follow to get more idea about ADC. Thank you, everyone. We are open for Q&A.
Thank you so much, Shriya, for the beautiful masterclass, the clarity in your explanation and, the practical example, especially the last few slides, The way you broke down the complex concept made the session extremely valuable for all of us. And also, Ashudeb, thank you so much for your presence and guidance throughout the session. And now it's time to take audience question. From the start only, the audience are putting the questions in the chat, so we can take it now. And the first question, Ashudeb sir, I would like to ask you. Prasenjit Samantha is asking that which roles are there for the semiconductor industry?
So, semiconductor industry, there is a designer engineer, there is a digital engineers, there is a then layout engineers, there is a verification engineers, and there is a basically test engineers. So 5-6 position is there in the VLSI industry on that, and on which direction you are moving on that. But it is an enormous areas, and it has a number of like different vertical, 5-6 vertical is there.
Got it. So there is one more question Mahavir is asking that what AIC stands for what? ASIC.
ASIC stands for Application Specific Integrated Circuits. So whatever application you are doing, based on that application, you have to put it on there. And that application, when you are defining in a particular chip, suppose you are designing a computer chip for processor, so that is a processor chip. Suppose you are looking at a display on that your computer, that is the display chip. You are listening the music or particular the audio chip. So that is the application specific integrated circuit.
Okay, I think Mahavir, I hope you got your answer. One more question, Ashudeb sir, is related to the program. And Nikhil is asking that is electronics qualification mandatory to pursue this program?
Electrical, electronics, instrumentation, or even computer science people also can attend that program.
Okay. And the Raj is asking that is it possible to apply AI/ML in VLSI design, and how we can get data set then if we apply?
Actually, data set in the very important thing in the suppose you want to design a SAR ADC in a very optimized way, or any chip you want to do optimized way or anything there. Your design itself data set you can create through a simulator. So that will be not a tested data. But simulation data you can utilize and you can optimize by AI algorithm in a faster basis. So there will be a lot of optimization happening respect to layout perspective, respect to design perspective, so that your design cycle will be reduced by AI/ML technique. But it is more like a data centric without understanding the inside of the circuits.
Got it. Same question, the other question from the same person, Ashudeb, that is VLSI design require coding?
Obviously, VLSI design circuit is require coding because it is a 1-0 thing on there, right? With 1-0 means there is a code is involved in there. So whole digital circuits and even associate that the digital and analog mixed signal level coding, as well as if you want to write down your test bench to be more efficient way, you have to write down a lot of scripting. So coding is there on the chip design.
Right. Sir, one more very common question which we get in every session of this program, that which is more in demand, market digital or analog VLSI?
See, what I'm telling, market demand is if you look, digital is say 60% to 70%, whereas analog is 30 to 40% on that. So digital is more heavy on that, but if you put in analog, you will be get a digital also.
Sir, Divik is asking that in program there is only theoretical or there will be practical.
We have a program of the online program which is theoretical, because online means theoretical as you understand. There is a quiz and assignment is there, but that's why we introduce bootcamp, which is practical, which is the first time in any IITs or any other thing they are starting that 1 week bootcamp. There is maybe long time bootcamp is there, a lot, long time something is there, but very quick. After theory, you are getting to the practical design hands-on in IIT Hyderabad.
Right, sir. So one more question anyone can, out of you can answer. That how many months it will require to learn the basics of VLSI?
To person, but I think that if you look at least 3 months is the kickstart. On that you can understand, but you have a real to move forward, you have to carry forward another 8 to 9 months. So 12 month cycle is required to understand the chip altogether. And then if you want to do tape out, testing, etc., maybe another 2 years. So 3 years is the cycle. You can able to understand complete design as a student on that. But if industry, it will be maybe lesser because you have a different environment, different set of things.
So Mahesh is asking that this certification course knowledge is sufficient for VLSI and semiconductor designer, and which role do you suggest for mechanical background after completing this program?
I cannot say this is sufficient for industry or this thing, but major thing is to that if you want to start something, suppose you want to take the, like you want to have a drink of water, you need a glass. Okay. So after that, you have to put your effort to fill the water, right? Basically. So we will be give you glass. And after that, you have to fill the water, then you will be able to drink the water. Okay. So this is the thing what we want to create I'll give you glass. Now your story will be complete with the drinking the water. Fill the water and drink it. And mechanical people, I'm not defined clearly, but mechanical people also take a lot of minor course in the electronics way. They may be these days, many of the like semiconductor chip design understanding help them to the semiconductor fab company in the mechanical domain. So these understanding help them basically.
So with this, I think we have come to the end of the session, and great to hear that. So with this, I would like to ask the last question to Ashudeb sir and Shriya. That we would be glad if you could share your final thoughts with our audience and tell them that why this certificate program will be beneficial for their career.
First of that, again, repeating, I am telling you, because VLSI is the new field, but if you go to Taiwan or China, that is a very common. Day-to-day people work that one, and that is the important part of them. So that's why I'm just telling you that if you want to make sure that what your mobile phone you are using, so even if you say some kind of your home you are using remote or any sort of gadget, whatever using, only possible if you have a chip design to innovation. Without that, it is not feasible, and that anything you want to do innovation. Because most of things imported and we assemble here. Some cases we even not assemble also. So the chip design aspect is the Indian upcoming days 10-15 years vision, and that will be the next market for a after software. That is the market, and good thing is that like software can you can change, but hardware changing is very difficult. If your knowledge of hardware one time happen, it will be moved forward. That's why China and Taiwan, you see, they are still at the ahead. Even US also ahead. India just started on that, and a lot of startup companies coming, a lot of MNCs there. So this will be gradually moving in the next direction because understanding is over from our side. Now government also initiating and a lot of other initiation is there. So we should have our indigenous chip. So that's why I can say that this is a field which is very upcoming.
So, Ashudeb sir, it's safe to say that it will be bringing in the unlimited job opportunities and career opportunities in coming years, or maybe it's already started, right, sir?
Already started because a lot of startup came and many startup is coming on India on the chip design level.
Right.
Not MNC anyway, they are there, but there is a lot of startup is coming to that direction.
Great, great. With this audience, there is one more announcement I would like to make that on 24th of September and 26th of September, there is an exclusive session for the audience. You have already got the invite for the session, and we will be doing live Q&A session. So whichever questions you have, queries you have, doubts you have, with respect to the topic, with respect to VLSI chip design, you can get your answers directly from the experts. So please don't forget, we will remind you, and please join the session. And we have the first session on 24th of September on analog design. So this is the news which I would like to share with all of you. So please join, and it will be a live Q&A session, the highlight. And also we will be covering this session and this program details as well in the session. Ashudeb sir, I would like to ask you the last question, that why do you think the certification which we have will help the audience to stand out in this, in the job market? As we already spoke that...
any of the thing on that, first I said IIT is a big brand. Okay. So
Right.
whenever you are doing that thing, that brand value is there. Along with the TCS is there, he will be always, you can reach them, what is the opportunity, what is the thing is there. That's why they have a very big global network. And this is the two combination, that's why we are bringing that certificate program. It is I can say at least you are moving out from a home, basically. You are moving towards like instead of sitting in a home, you are searching, at least you are coming out that let's take the steps and coming out home. And this kind of IIT brand at least help you in the next level on that. But obviously, I said you that this is some kickstart. After that, obviously, our people are there to mentor and follow up on that. But you have to do a lot of hard work on that. And maybe this will be give you IIT opportunity. Who knows that whatever our MTech program across the all IIT, not only us, only IIT Hyderabad, there is a maybe 200 to 300 self-sponsor program right now, even more than that. So if the people have go through that, they have a IIT certificate, they are very much know that these people has gone through that at least fundamentals and whatever thing they have learned, at least IIT professor has taken those notes on that.
Right, sir. Well said. Shreya, we would like to know your thoughts as well, that why do you think, the certification like this, which we are having, will help student to get the, in the job market, to stand out in the job market?
So the most important thing I've seen, whether you go for analog design engineer, digital design, verification, physical design, there are many roles, 6, 7 roles are there for the freshers. So in all the roles, the most important thing the industry requires is your fundamentals. They first focus on your fundamentals. You might think that okay, digital electronics, you already know RC circuits. But if you understand the fundamentals, the basic working behind as basic as RC circuits, if you understand the networks and the circuits properly, you can apply the skills you will learn here on the transistors, on the transistor level schematics or circuits as well. You might think that, okay, ADCs are very complex and it's difficult to start with designing them. But after learning the fundamentals, you can design any circuit, any schematic you come across with. So I hope you guys will clear all your fundamentals. Those are the most important parts. All the best to all of you.
Thank you so much, Shreya. Ashudeb sir, Nihal is asking that what is the current trend in the industry of VLSI design engineer? And he's from EC background. And I think, as per his question, I think he's asking that what kind of topic we will be covering in the program to help him get placed in good companies.
Again, I'm telling you that whatever the scopes on that, it will be covering fundamentals and cover you the steps to understand what is the practical aspect of that thing. And then whenever we are bringing to boot camp, you understand how this SAR ADC or this one of the problem statement or subsection of the problem statement, how design has been carried forward. So these will be industries looking also that you should be a more practical oriented. And then you have to take in the next level when you reach to your suppose your institute, you should carry forward those things, more details, more understanding level, and that help you to get a job.
Great to hear that, sir. So with this, we'll come to the end of the session. A heartfelt thank you for Professor Ashudeb sir and Shreya for taking us through such a wonderful session on 12-bit SAR Asynchronous SAR ADC. So I think we all agree that it was truly insightful and eye-opening session. To all the students here, moments like this where you should start thinking seriously about your future. So the chip design, as I said, this industry is booming, and opportunities are only going in and multiply in the coming years. So if you build your foundation now, you'll just not be job ready, but you'll also stand out in this competitive field. And that's exactly why this program is designed to do so. So I encourage you all to please take the next step and enroll for the program. So with this, again, I would like to thank Ashudeb Dutta and Shriya. It was pleasure to have you with us today. And we sincere appreciate your time and presence in today's session. Thank you so much. Thank you, lovely audience, for active participation. Have a pleasant evening.